Okay then, good evening everyone. Let's start with today's session, today's tutorial for the fourth week. Let me share my screen. Is my screen visible to you guys? Anyone please answer me?
Yes, ma'am.
Okay. Okay. So let us start with today's session. What we will be talking about today will be the content for this week is the various impurities which are present in the liquid fuels, as we have talked about liquid fuels last week, petroleum like crude oil and its various products. So this week we will be talking about various impurities that are found in various crude and liquid fuels and the different routes, conventional routes to purify these liquid fuels from these impurities, as well as the various modified and improved versions, improved routes for the purification of crude oil from these impurities. So, firstly, we will be talking about various impurities that are present, such as sulfur, nitrogen, metal, and various procedures that are used for the removal of sulfur, nitrogen, and demetallation. Then the various residues that are produced from the petroleum residue, petroleum product, crude oil. Then it's then removal, or we can say the just a second. In various residue upgradation rules, such as solvent deasphalting, how to remove the asphalt that is present in the crude oil. Then visp breaking, delayed soaking gasification methods. Then the heavy crude is that we get from the crude oil after the atmospheric distillation and vacuum distillation. We get heavy crude oil, its various properties we will see, the problems that are associated with its refining, and the conventional refining flow sheets associated with heavy crude oil. Then the modified flow sheet, the modified refining configuration, we will be talking about it, how modifications are done in the various refining flow sheets, various refining procedures to for the easy that purification of this heavy crude oil and for easy extraction of valuable products from these heavy crude oil. Okay, so then let's come to the impurities and need of their removal. So why do we need to remove these impurities? So basically what happens is the crude oil, it consists of various impurities, such as sulfur content is present, nitrogen content is present, then salt is present, and metals are present. But all these are considered impurities and degrade the quality of our products that are derived from the crude oil. So these needs to be removed. Then the another problem is that nowadays the crude oil that we are getting, its quality is degrading day by day. The sulfur content and nitrogen content and metal content is increasing in the crude oil that we are getting in nowadays. So which further on when we refine them and produce various byproducts such as gasoline, LPG, and kerosene and diesel, they also consist of considerable amount of impurities. That is basically the removal of this large amount of impurity on a very finest degree is not that possible. So, in turn, these impurities create more pollution in the environment and also degrade the quality of the final product. So, basically, the most common impurities that are present in crude oil is sulfur, then nitrogen, then some salts, and then metals. So, firstly, we will be talking about the removal of sulfur content from our crude oil. So, as we studied earlier also, that sulfur is present in both organic and inorganic form. So, removal of sulfur is basically uh, done by sweetening procedure, which is by alkali extraction. So, sulfur is present in the form of basically H2S, which is acidic in nature. So, if we neutralize this acidic H2S by using some kind of alkali, that is by using some kind of alkali such as NOH, so by neutralizing, we can remove this sulfur from the crude oil. So it is basically done by two ways. The first one is alkali extraction, that is caustic sweetening, and also hydro treatment can be done. So let us come to the various caustic sweetening procedures. The first one is caustic wash. In this procedure, simply what we take is we take a caustic solution, basically a sodium hydroxide solution, and we wash our this caustic solution is basically it is called caustic lye, and we wash our crude oil with this caustic solution, and this reaction here, this RSH is basically the sulfur present in our crude oil in the mercaptan form, and when we add NOH in it, it forms sodium sulfide and water. And after the mixing, what happens is the separation of the organic and the aqueous layer takes place. The mercaptan in along with the sodium comes with the aqueous layer and the that oil layer, which is our crude oil layer is separated from the mercaptan. So two layers form, and then we can separate them. So basically, caustic solution is used in the range of 5 to 28% caustic solution is used at a temperature of 20 to 45 degrees C and 5 to 40 psi pressure. High temperature and strong caustic acids are not used. Very light caustic acids are used, because if we add strong caustic acid, then there is risk of color body formation and stability losses is there. Therefore, that light caustic acid is used. So another term, spent life. So when we add this caustic solution into our crude oil, not whole caustic solution gets used up. Only about 60 to 65% of the sodium hydroxide solution is used in the formation in the removal of hydrogen sulfide. So this used sodium hydroxide solution is called spent lye, and mm, it is not that this used sodium hydroxide solution cannot be used further for the removal of other impurities. It can be further used for the removal of minerals or organic acids from petroleum products. The second procedure is doctor treatment. So it is the procedure in which it is a treatment with sodium plumbide solution. It is the treatment with sodium plumbide solution, Na2PbO2, and elemental sulfur is converted to disulfide. So this reaction takes place. This is the mercaptan which reacts with the sodium plumbide and form PbSr whole twice and NaOH. Further, this sodium that PbSr2 whole twice again reacts with the elemental sulfur to form disulfides, and this PbSr2 whole twice is again, if there is oxygen present, then it oxidizes to disulfide and PbO. So too much sulfur, excess sulfur cannot be used in this, because it forms if we use excess sulfur, then it leads to the formation of polysulfides, which leads to the which causes more corrosion in value of our petroleum products. And moreover, if we use very less sulfur, then then the oxidation of PbSr2 takes place, which leads to the formation of PbO in our that remains of Pb lead oxide in our crude oil, which leads to the failure of water tolerance test of our crude oil, basically degrading its quality. The third procedure is copper sweetening. In this, it is the treatment of copper chloride in this copper chloride is used, chloride is used for the conversion of mercaptan to disulfide. So the reactions taking place is here mercaptan is reacted with cupric chloride to give CuSr and HCl and means sulfide as well as disulfide. Then further, mercaptan is reacted with CuCl to give sulfide. And then this copper sulfide is further reacted with cupric chloride to give disulfide. And this copper sulfide on oxidation leads to the formation of copper oxide as well. So here also the problem is if we use less copper, then oxidation may take place, leading to the formation of copper oxide, which further leads to the failure in that water tolerance test. And then copper chloride, if some oil soluble and sometimes this cuprous mercaptide, which is sometimes oil soluble, also remains in the treated oil. That is a problem. And copper chloride reacts with naphthenic acids, that CuCl reacts with naphthenic acids, phenols, and other polar compounds to form oil-soluble copper compounds, which is also a problem. Since so this method had some disadvantages. That is, it led to the remains of some amount of copper into our petroleum product, thus leading to the degradation of its quality. So this is the just a second. This is the procedure which is the which is the most used method for the removal of sulfur. That is the MEROX process. It is one of the most successful treating processes licensed by UOP, which was introduced in 1958. And this method completely replaced all other methods. It is one of the most simple and economic procedures. So what happens is in this extraction of in this extraction of both low molecular weight mercaptans as well as high molecular weight mercaptans is possible. That is the low molecular weight mercaptans, which is produced from low molecular weight products such as LPG, light straight run, naphtha, with and high molecular weight mercaptan, which is derived from heavy products such as heavy naphtha, FCC, gasoline, ATF, etc., can be converted to disulfides and removed. So the mechanism taking place here is this mercaptan on reaction with NaOH gives sodium sulfide, which is soluble in water, so it goes in the aqueous phase. And this sodium sulfide on oxidation gives sodium hydroxide and disulfide. And this mercaptan, on further oxidation gives disulfide and water. So this first reaction basically is for lower molecular weight mercaptans and and these two reactions for higher molecular weight reaction. So coming on to the MEROX procedure, this is a flow sheet of MEROX process. So what happens? We take the feed here, the feed which consists of sulfur impurities. So caustic wash is done here to remove the inorganic sulfur. It is done here, and uh, sulfur is removed from below, and further after caustic wash, this product goes to the extractor, where further on treatment with caustic solutions, as told in caustic solution, that is sodium hydroxide mainly, is done here. On caustic treatment, the lighter products, basically free of mercaptans, are released from above, and the mercaptide rich caustic solution, the caustic solution after taking the sulfur compound, will be going from here and here, after it is at high pressure, uh, it will be going from here to this oxidizer, where on introduction with air, it will be further oxidation will be done according to this reaction. This third one, oxidation takes place to convert this mercaptide rich caustic to disulfides, and and further after oxidation, the product goes to the disulfide separator, where if some spent air is there, this excess air it is released from above, and this disulfide separator, there will be two phases, that is the aqueous phase and the oil phase. So the disulfide, which is the oil phase, will be extracted from above, and the aqueous phase consisting of the regenerated NaOH will be taken back to this extractor, where it will be further used for caustic washing. And this lighter products, which also consisted of some amount of NaOH, their caustic settling will be done. And by passing through the sand filter, if there are some other caustic in NaOH solutions left, then in this sand filter it will be removed, and we will be getting a lighter product from here. Now coming on to the other procedure, as I told that not that sweetening procedure is used, and further the another procedure is that hydrotreating procedure is used to remove the sulfur. So processing, basically it is a thermal conversion in which hydrogen is used to basically we introduce hydrogen in the presence of high temperature. So hydrotreating, in this, hydrogen is used to convert heteroatom some constituents into heteroatom hydrogen analog and hydrocarbon. So basically, mercaptan on production with hydrogen will be converting this heteroatom constituent into heteroatom hydrogen analog, which is hydrogen sulfide, and hydrocarbon will be produced. So, and another is hydrocracking. In hydrotreating, what we do is we just introduce the hydrogen. No cracking or conversion of higher molecular weight constituents to smaller molecular weight is done. But in hydrocracking, it's conversion or decomposition of higher molecular weight constituents to lower molecular weight constituents is done. So which is the thermal decomposition is extensive and hydrogen assisted in the removal of heteroatoms such as sulfur and nitrogen, as well as mitigating the coke formation. So in hydrotreating and hydrocracking, one major difference is that in hydrotreating no coke formation takes place, but in hydrocracking, sorry, in hydrotreating coke formation takes place, but in hydrocracking coke formation is not taking place, which normally accompany. Uh, and this procedure normally what it does is it cracks higher molecular weight constituents to lower molecular weight constituents, and further by addition of hydrogen, convert them into a stable product. The major difference between hydrotreating and hydrocracking is basically the difference of the feeds is at which the feedstock remains at reaction temperature is different, and extent of decomposition is also different in both hydrotreating and hydrocracking. Third thing is metal removal, another impurity which is found greatly in our crude oil is the various metals such as sodium, potassium, lithium, calcium, strontium, copper, silver, vanadium, magnesium, tin, lead, cobalt, titanium, gold, chromium, and nickel. And mainly vanadium and nickel are present in the crude oil. So the concentration of these nickel and vanadium varies. Vanadium is found as low as zero point 0.1 ppm to as high as 1200 ppm, and nickel varies from traces to 150 ppm. And vanadium and nickel are present in basically two forms in our crude oil, basically porphyric and non-porphyric state. And basically, what till now porphyric forms are mostly explored. Non-porphyric forms are still not explored, and uh, this is the structure basically. An estimated structure of porphyric states of metals which are present in our crude oil. This is a formula, and its molecular weight varies from 420 to 520. So the removal or of metal, or basically what we call it demetallization, can be done in various forms. So physical method is basically deasphalting can be done. So metals will be remaining with the asphalt left down. And the chemical methods are this breaking, smoking, and chemical and more chemical and various chemical treatments can be done. So in deasphalting, what we do basically, what is done in if we do solvent extraction. So when the solvent mixes with the asphalt. So the lighter portions of the crude oil that gets dissolved with the solvent and is uh, separated from the heavier asphaltenes. Along with that, the metals are also remain with the asphalts. So one form is this, the other forms such as visbreaking and coking. And the basic chemical concept of demetallization, which here we will be talking about, is the removal of metal from the organic moiety with a minimal conversion of the remaining petroleum. So basically, if we use the demetallation of a metal for if we you uh, what we have done is porphyric metal is treated using a acid which is HX, and this metal is converted. Porphyric metal is stabilized, and metal metal salt is formed. That is, this is metal, and with the treatment of acid, this it forms the metal salt of the porphyric metal. So catalytic, so this is also a procedure of removal of metal. Another procedure is we can remove the metals by hydroprocessing as well. That is by the addition of hydrogen, by the treatment of the crude oil with hydrogen. Coming on to the next section, that is petroleum residue and its upgradation. So basically, as we know, the crude oil we get from the below the earth. So this crude oil is first sent to the atmospheric distillation unit, from where we get the atmospheric residue. Then this atmospheric residue is sent to the vacuum distillation unit, from where we get the vacuum residue. So we can see that the quality of these residues will be degrading gradually, so that the crude oil will be having the better quality than atmospheric residue, and then the vacuum residue will be having the worst quality. So as we are doing the treatment, so as we know that after doing the treatment, the lowest grade quality product will be given out as residue. So after first treatment, we get atmospheric residue, so its quality will be degraded in comparison to crude oil. Then after second treatment, that is vacuum distillation, we will be getting the vacuum residue, so its quality will be worse from the in compared to atmospheric residue and crude residue. So here also it shows the same thing, that with degrading quality, viscosity increases, sulfur content in the crude oil as well as residue as well as increases, nitrogen content increases, then asphaltene percentage also increases, hydrogen to carbon ratio decreases. So hydrogen to carbon ratio is inversely proportional to the quality, and API gravity, as we know that higher the API gravity, the better the quality of crude oil. So we can see that as the degradation of the quality is taking place, then the API gravity is also decreasing, and carbon contracts and carbon residue is increasing. So the residual oil differs from the average crude oil. So basically, the residual oil, which is after the vacuum residue, It has so with the degradation of quality, what happened? The viscosity increases, sulfur, metal, and asphaltene content increases, average boiling point increases, hydrogen to carbon ratio decreases, and contraction carbon ratio increases. So essential requirement for gradation is improved properties. That is, we have to increase the hydrogen to carbon ratio if we want to improve the quality of the crude oil or the products from the crude oil. So coming on to the residual oil which we are getting. So a residual oil can be, it is basically a colloidal system which consists of maltines, asphaltenes, and resin. Basically, we are talking about the vacuum residue which we get from the vacuum distillation unit. It is kind of a colloidal solution in which we have three things. This is a kind of an emulsion which consists of asphaltenes, some resins, and the continuous phases, these maltines. So these maltines are basically the oil which we want, which is the lighter product, which the better quality product which we want compared to these asphaltenes and resins. So we want these maltines. So what we will be doing to extract these maltines, we will be talking about here. So what we will be doing either by thermal cracking or by solution extraction, various methods are there to extract these maltines. So in suppose we take the thermal cracking method, so what happens? The oil phase cracks, and after certain limit of cracking, the colloidal if we use the thermal cracking, so this emulsion starts to this oil phase starts to crack, and after certain limit of cracking, this colloidal uh, right now we can say that this colloidal system is in equilibrium. But after thermal cracking, after certain limit of cracking, this equilibrium breaks, which results in this separation of asphaltenes, resins, and maltines, and we can get the maltines. So at this stage, cracked fuel oil becomes unstable in nature and some physiochemical properties. After so- so the residue we will be getting, it will be having higher viscosity and higher salt content, higher heavy metal content, higher sulfur and nitrogen content, and high naphthenic acid. So there are various routes of upgradation, mean uh, routes to extract the lighter fractions from these residue oil. There are various fractions, various methods to do so. So basically, the it consists of three techniques. The first one is hydrogen addition, then carbon rejection, and some other techniques. So hydrogen addition is basically we add hydrogen, we introduce hydrogen, which is hydrodesulfurization, hydrocracking, and it is done in three ways: fixed bed, evaporated bed, and slurry bed. And the carbon rejection method is that is removal or subtraction of carbon basically, which is thermal cracking or catalytic cracking. Thermal cracking is two types, that is visc breaker and poker. And catalytic cracking is FCC and RFCC, that is fluidized catalytic uh, cracking and residual residual fluid catalytic cracking. And the carbon rejection third method is solvent extraction, which is solvent deasphalting. Another techniques include gasification, that is conversion of liquid fuel into gaseous fuel. So the first technique we will be talking about is this solvent deasphalting. So what we do is we will take the vacuum residue which will be given by the vacuum distillation unit and these into solvent deasphalting unit. So it will be so what here is done, we introduce a solvent and mixing is done. So the lighter fractions, that is the de-asphalted, that the remains subtracting the asphaltenes dissolve with this solvent. So it is and the heavier fractions settle down in the form of pitch. So two phases will be formed here. So we will be taking out the de-asphalted oil from here, which is further sent to for further processing into FCC or hydrocracker or thermal cracking for its further processing and improvement of its qualities. And this heavier fraction, which consists of various impurities such as metals and asphaltenes, in the form of pitch, is further processed to give out bitumen or that is for the construction of roads, then to CFBC for power generation, then for the in the gas further this heavier uh, product which is pitch can be gasified also the uh, for the power generation, for steam and hydrogen production of petrochemicals and fuels. So this is de-asphalting flow sheet for a de-asphalting unit. So we take the feed, which is our vacuum residue basically. We along with the solvent, either the fresh solvent for the first time, and after that, after starting of the unit, the solvent which is taken is the recycled solvent after each cycle. Will moreover renewal of the regeneration or addition of fresh solvent time to time is also done. Uh, So mixing is done here, and as we know that its viscosity is very high, so it will be pumped into the extractor using a pump. And here in the extractor, mixing of this solvent and feed will be done. And sometimes some temperature or pressure is given for the proper mixing. In so we will be getting two phases here. The lighter fractions will be going here. Heat recovery will be done here, and then it will be sent to DAO separator. And the heavier fraction consisting of asphaltenes here, or after the heat recovery, it is sent to the pitch stripper. That is, even if this pitch consists of some amount of solvent, so the heavier fractions will be given out from below, and the lighter fractions will be taken from here. For the solvent recovery, it will be sent to the mixer and then condenser. And after the solvent recovery, the solvent will be again gone back, taken back to the initial stage for further de-asphalting. And then after and from here the de-asphaltene oil separator, it is sent to the de-asphalting oil stripper, where de-asphaltene oil is taken out, which is the lighter fraction product, which is our basically our desired product. Either we can use it in the same way. Basically, it is not used in the same way. It is further processed for to extract various products such as LPG, kerosene, etc. And and this de-asphaltene oil is given from here, and from above the uh, our solvent, if some amount of solvent is also present here, that is extracted from the above side and sent to the mixer and condenser for further recovery of the solvent, which is from here sent back for further de-asphalting. Coming on to the various de-asphalting solvents which are used, commercially used solvents are such as propane, butane, pentane. Sometimes hexane is also used, but it is used rarely. So lighter solvents such as propane and isobutane. So lighter solvents, it has better selectivity for our lighter products. So if we use these propane and isobutane, as they are smaller molecular weight solvents, so they will be dissolving the lighter products more easily, thus rejecting all the resins and asphaltene. So as their molecular weight is lower, so they won't be solubilizing any amount of resins and asphaltenes. Thus, it is suitable for the production of lube oils, has higher selectivity, as I told, that it has better selectivity for lighter products. So heavier, if and another is heavier solvent, that is N-butane, pentane, and light naphtha. So they have less selectivity for lighter products. So it may also dissolve some amount of asphaltene. So produce higher yields of the asphaltene oil. Well, the general properties, that is, if the solubility of the oil decreases, if we increase the temperature if we move to a higher temperature, then the solubility of oil decreases. More selective at higher temperature and exhibit lower critical solution temperature. Coming on to another technique after de-asphalting, that solvent extraction for de-asphalting. Another technique which is widely used is the vis breaking. So, as the name itself tells, what is vis breaking? Uh, it is basically Vis breaking is basically decreasing the viscosity by cracking, or basically breaking is by decomposing higher molecular weight compounds into smaller molecular weight compound, which in turn will also decrease the viscosity. So it is basically a mild, predominantly liquid phase thermal cracking procedure where high molecular weight hydrocarbons are broken thermally into lower molecular weight ones, yielding products of low viscosity and low pore point. So petroleum residue is converted to small amount of light hydrocarbons such as LPG, naphtha, gasoline, etc. A and residual part with reduced viscosity. It has been developed to produce fuel oil, resulting in saving the valuable lighter products called cutter stocks. So the mild operating conditions are that feedstock are heavy, and so why mild operating conditions are used? So the mild operating conditions are used because we just want a small breaking of the higher molecular weight to smaller molecular weight products, but if we provide more temperature, so here heavier products are also there, asphaltenes are there, so if we provide higher temperature, then coking may take place. Allowable conversion to gasoline is lower in visbreaking due to fuel oil stability requirements. So this is a visbreaking mechanism. It is a complex procedure. It basically takes place in three steps: initiation, propagation, and termination. So basically, if we take this higher molecular weight product, it will be producing on thermal on heat treatment, on thermal cracking, mild temperature, it will be producing radicals, have a smaller molecular weight radical and a higher molecular weight radical. Further, these radicals will be propagating in by reacting with other hydrocarbons, such as this smaller molecular weight hydrocarbon will be reacting with this hydrocarbon to produce a smaller molecular weight hydrocarbon, and a larger molecular weight radical. And likewise, this may react with this to form smaller molecular weight hydrocarbon of C4H10 and higher molecular weight hydrocarbon of C6H13. So likewise, the moreover, these radicals can also further uh, uh, crack into stable products such as C4H8 and a radical. As we can see here, this is cracked to C2H4 and a radical. So, likewise, propagation takes place and further termination takes place by the joining of two radicals, as this joins with this to give C2H6, CH3 with H positive may react to give a gas which is methane. That is, gaseous product may also. So, in this form, this breaking takes place. So, we can see here that larger molecular weight produces a smaller molecular weight product. Thus, we can also see that the even phase change can also take place. Am I audible to you guys?
Yes,
Hello.
ma'am.
Okay. So even phase change can also take place. Moreover, viscosity decrement in the viscosity also takes place. So this is a flow sheet of this breaking. So we take the preheated feed, which is further taken to the furnace where thermal cracking takes place. And this is a soaker. This we will be talking further, which is optional as it is written. I will tell you why. And further, this after heat treatment into the furnace, it is taken to the fractionator where, due to the difference of the boiling point, it is given into various cuts such as LPG, gasoline, gas oil, and the heavier product in the form of tar is further sent to a vacuum fractionator where, in the presence of vacuum, it is further fractionated into heavy gas oil and vacuum flash. The furnace is normally coil type, and furnace inlet temperature is 305 to 325 degrees C and pressure is 15 to 50 bar. and furnace outlet temperature is 480 to 500 degrees C and pressure is 2 to 10 bar. And residence time here is almost 2 to 5 minutes and steam injection is 1% volume. So let us talk about what is soaker. So basically, this breaking takes place in two ways. The first one is either you provide higher temperature for smaller time, and the second one is either you provide the smaller temperature for a higher time. Two ways it takes place. So when we use higher temperature for smaller time, then this uh, furnace provides higher temperature and the residence time of the heat is very less here. After thermal cracking at a higher temperature for smaller times in the furnace, it directly goes to the fractionator. But when it is done at smaller temperature for higher time, for a larger residence time, so what happens is here in the furnace, the feed residence time is very less for at a smaller time. In thermal cracking takes place in the furnace, and after that, it goes to the soaker where it stays for larger time period at smaller temperature, and after that it goes to the fractionator. So to reduce the furnace temperature, a soaker unit is basically furnace temperature is high only, but when we want the this breaking to take place at smaller temperature for large time, so in the furnace we keep it for a smaller time, and after that it goes to the soaker where temperature is lower and it stays there for a longer time. To reduce the furnace temperature, a soaker unit is placed between the flash chamber and furnace. Temperature and pressure maintained at soaker unit are 440 to 460 degrees C and 5 to 15 bar with 20 to 30. So, as I have told here that in the furnace residence time is only 2 to 5 minutes, but here the residence time is very high, that is 20 to 30 minutes residence time is there. Preheating of the feedstock is done up to 335 degrees C by using this breaking tar. So this vacuum flash tar, it is not thrown away. It is further it can be used for the the heat from this can be recovered for heating up our feed here in preheat. The overhead product of the flash chamber gives naphtha LPG as I have shown here. It gives LPG, gasoline, gas oil, and the bottom product is further fractionated into gas oil and residual product. Through this procedure, around five-fold viscosity, as I told that it is this breaking, so viscosity reduction takes place up to 5 times when 5 is possible when 5 to 10% naphtha is produced. Depending upon the reactor design, this procedure can be classified into two categories: soaker visc breaking and coil visc breaking. So soaker visc breaking is this. Sometimes this soaker drum is used, but sometimes instead of the soaker drum, a coil can also be used instead of this soaker drum. Here it will be for a kind of a coil to increase the residence time of the feed. The soaker visc breaking procedure is a relatively low temperature procedure with relatively higher residence time. As I told you, the soaker visc breaking in the soaker drum, low temperature is there for a higher residence time. And for coil visc breaking, the resident and for coil visc breaking, the residence time is much higher, which is 1200. Sorry, less residence time, 100 to 300 seconds for coil visc breaking, and more residence time, 1200 to 1800 seconds for soaker visc breaking. So even here, soaker visc breaking 20 to 30 minutes. But instead of this coil is used, then residence time is lesser. Coming on to next technique, which is the delayed soaking. Soaking basically, we know that it is the basically cooking happens in the thermal when thermal cracking of the crude oil takes place, then it and some residue that spongy material residue is left after the thermal cracking, which is basically coke. So delayed coking is basically we do the coking, but uh, residence time here is more. So term delayed refers to the delayed reaction which initiates in coil furnace. but completes in coke drum by delaying the procedure. So basically, taken for coking here is more. A severe thermal cracking procedure aimed at upgrading of petroleum residue by converting it to liquid and gas products, predominantly uh, relatively inexpensive considering open art and companies to. So delayed coking basically it happens in two ways. Decomposition of large molecules to smaller molecules takes place, and secondary reaction if products such as aromatics, active products from primary cracking reaction further crack or react to form other products or polymerize to give heavy products. So basically, this is the thermal cracking of large molecular weight, basically asphaltenes, the heavier products, heavier residue which get the thermal decomposition of these heavier products when they release scope. It is basically done from the decomposition of this heavier products such as asphaltene. But these active products are basically when by initial cracking some kind of lighter products are formed such as we get aromatics or unsaturated products, they further combine to polymerize and give coke, which is better quality coke. So this is the secondary reaction is that. The two type of mechanism, very higher molecular weight compounds, as I told, that asphaltenes and resins tend to decompose when they are subjected to high temperature. So and when they are subjected to high temperature and produce a highly cross-linked structure of amorphous coke. So the coke produced in this method, in this mechanism, is amorphous in nature. And the second procedure is the polymerization and condensation of aromatics, as I told, throwing a large number of these compounds to such a degree that eventually coke formation takes place. So the coke formed in this contains fewer crosslinks and has more crystalline appearance than the resin asphaltene coke. So the coke produced in the resin asphaltene type of coke, which is amorphous in nature, this coke is more crystalline in appearance. This has a more orderly structure. So basically, due to this orderly structure, they produce a very fine quality coke. So due to its amorphous nature and high, so in the heavier coke of the asphaltene coke, due to its amorphous nature and high impurity concentration, the coke produced is not very desirable. But the coke formed from the feedstock containing high concentration of aromatics and low concentration of resin asphaltene, this premium grade coke and this type of coke is called the needle coke. The term applies because the particle appears like as well, they are basically in the form of needle, and the coke produced from asphaltenes they are basically in the form of sponge. So the feedstock in delayed coking is basically the vacuum residue, as we all know that all mainly vacuum. We are processing mainly vacuum residue, but sometimes atmospheric residue is also processed. Typical feed consists of 6% sulfur, as I told you, it consists of sulfur impurities, some metals, which is about 1000 ppm of metal, chondroitin carbon ratio of about 20 to 30%, and feed ultimately depends on the type of coke desired. So basically, the product consists of copper gas, C3, such as LPG, and lighter ends can be used as fuel gas. And the liquid product, which is naphtha, contains high olefin content, and heavier liquid product gas oil, which is basically gasoline, diesel, and jet fuel are produced. And the coke, as I told, the finer grade coke, which is produced by the polymerization of aromatics, this is the needle coke, which is basically you can see it is in the form of needle. And the coke produced from asphaltenes and resins, these are two, which is the first one is sponge coke and the second one is short coke. It is basically in the form of sponge and spongy structure it is. The And due to its very fine structure, its very fine qualities, it is widely used as electrode material as well. This needle coke is widely used as electrode material. Coming on to the flow sheet of delayed coking. So we take from here. From here, the fresh feed is taken to the fractionator. Along, uh, just a second. So from here, we take the feed. It is sent to the coke drum. Then it stays for some times stays for some times, and cooking takes place. And further, after cooking, the heavier products are sent to the heater along with the steam. And here, it is due to the high viscosity is pumped to the fractionator using a pump. And this heated feed along with the steam is in the fractionator. It is after the fractionation, it releases the lighter products, which after heat recovery and after all the heat recovery, the lighter products are given as gas, which may be basically LPG or fuel gas, etc. And the unsaturated and some of the part is given as unsaturated naphtha. And moreover, some of the lighter products also consist of some gases, which on gas stripper, which after separation is given out as gas oil. And further, and from here in the in the coke drum, after some time, this coke is given from here. Coke and liquid yields may be these are some of the empirical reactions which tells us about various yields of various products from the coking unit. So, coke and liquid yield may be estimated by simple equations such as coke yield is given by 1.6 into weight percent of condensate carbon ratio. Then gas weight ratio is given by 7.8 plus 0.144 into weight percent of condenser carbon weight ratio. Then gasoline weight percent is given by 11.29 plus 0.343 into condenser carbon ratio. Gas oil by 100 gas oil percentage can be given by 100 minus the content, the coke yield, gas yield, and gasoline. And the gasoline volume percent is given by this formula 186.5 upon 131.5 has API gravity into weight percent of gasoline. And gas oil volume percent is given by 155.5 upon 131.5 plus API into weight percent of gas oil. But the last technique which is used is the gasification techniques, as we studied in the coal also gives gasification is basically conversion of a solid or liquid product into gaseous product. So here also the residue, the gaseous liquid products or the vacuum residue on uh, on uh, on treatment with high temperature and pressure is converted to syngas to produce syngas through gasification. So vacuum residue and pet coke can be used to produce syngas through gasification. Since pet coke is very hard and less reactive, requires high temperature, and drain bed gasifier can be used. An IGCC concept which we studied in the coal is more attractive for gasification. So gasification is, since we studied it in detail during our the production of energy from coal, it is not explained in much detail here. Now coming on to the fourth section, which we will be talking about heavy crude oil. So basically, the heavy crude oil is the heavier part that we get. That is the last that after residue, after processing of the vacuum residue, we get. Just a second. Just okay. 2 minutes. Give me 2 minutes. लाइट नहीं आ रही है क्या? लाइट नहीं आ रही है क्या? मेरा लैपटॉप क्यों नहीं चार्ज हो रहा? देवी आप बंद करके चली गई। जगह जब बंद करके जल्दी जल्दी बंद कर बंद कर। सॉरी फॉर द डिले। Am I audible now? Anyone please answer me? There was some power issue, that's why I had to go. Am I audible?
Yes, ma'am.
Okay. Okay then. So let's talk about heavy crude oil. So basically, till now we were talking about the extraction of valuable products from our vacuum residue, but even after that, after extracting uh, all kind of valuable products from the vacuum residue and atmospheric residue, some amount of heavy crude oil will be still left. So here we will be talking about that heavy crude oil. So as I told that the higher the API gravity, the more is the quality of the product. So as we can see here in this table, these are the lighter oils, medium heavy oils, and extra heavy oils, and bitumen. So basically, bitumen is the heaviest of them all. So we can see that the API gravity is decreasing as we increase, as the uh, products are becoming heavier. So the unconventional oils from enhanced oil. So not only these bitumen and all are these are natural crude oils, but nowadays various synthetic crude oils, synthetic crude is also available from the nature, that is in the form of tar sands and shale oils, also considered as heavy crude, and they produce synthetic crude. So synthetic crude is the output from a bitumen or extra heavy oil upgrader facility used in the connection with oil sand production. It may also refer to the shale oil and an output from oil shale pyrolysis. So shale oil is basically, it is the oil produced from a sedimentary rock. Basically, shale is a sedimentary rock. So in this figure, we can see that bitumen and heavy crude oil consist of asphaltenes, but synthetic crude it does not consist of asphaltenes. But in this saturates, we can see that such amount of saturates in bitumen is very less. In heavy crude, it is saturates are present, but in synthetic crude, large amount of saturated products are present. Saturated as well as aromatics is also present in a very large quantity. So the problems of heavy crude oil and its refining. So the problems with the conventional refinery units in processing heavy crude oil. So what were the problems that were uh, encountered in the conventional units in the past? So basically, it has higher viscosity, higher total acid number, higher sulfur content. Pipeline transport is very difficult due to its high viscosity, not compatible with conventional refineries. So what is done? This heavy oil is mixed with some kind of diluent, some kind of solvent or naphtha or anything, which reduces its viscosity a bit, not very much, but a bit. It reduces its viscosity. The heavy oil and diluent is mixed, and then through pipeline it is sent to the refinery. This is from the generation unit of the heavy oil, and then it is mixed with diluent, and this mixed diluent and heavy oil is sent through pipeline to the refinery, and further in the refinery various Processing is done to produce various transport fuels, fuel oils, or coke, and most of the asphaltenes. In different grade of products, high value and low value grade products are produced in the refinery here. Various products such as coking, disc braking, de-asphalting is done here. So basically, problems associated is that high crude side pressure drop. So as I told that its viscosity is very high, so it needs to be pumped through the pipeline. So due to this pumping from the production side to the refinery, there is huge pressure drop. Desalters upsets and poor desalting because salt quantity is very large in this, so desalting becomes very difficult. Rapid crude column and condenser corrosion due to these impurities. Corrosion problems takes place in the fractionation columns. Low diesel product is produced from these because they obviously diesel is a lighter product, so very less lighter products are present in these heavy crude. So low diesel products are produced. Vacuum heater coking and vacuum column fouling. So likewise here and here same problem is there due to these heavy crude oil, huge impurities, fouling and corrosion problems occur. So and high vacuum in vacuum distillation unit due to the higher viscosity and higher viscosity, high vacuum is required in the vacuum distillation unit. Lower HVGO product, drawn temperature, lower yield. High metals are present. As I told, impurities are very large. General corrosion problems, as seen here and here. This is a general problem that in all the equipments, corrosion problems will be there due to the high viscosity and impurities and metal impurities present. Heavy crude oil processing. So for processing crude oil, operational changes are made. Higher heating temperatures. So obviously, the processing of this heavy crude can be done only at higher temperature. Lower atmospheric and vacuum distillation operations means lower atmospheric and vacuum column operating pressure. Obviously, vacuum needs to be increased. So it will be done at high. So lower atmospheric column over flash. Flash products will be means over flash means the lighter products are given out in the over flash. So in these heavier products, lighter products are very less. Improved wash section efficiency, better ATB and VTB stripping are needed to maintain product yield and quality. Coming on to prerequisites for processing. Prerequisites for processing high acid crude. So basically, there are different kind of crudes. So if there is high acid crude, then suppose if below 0.6 tan number modification, crude blending can be done. Tan is total acid number. So if high acid crude is there, neutralization by alkali can be done to improve its quality and to help with the additives can be added to control corrosion problems and metallurgy. Basically, the equipment or the fractionator made should be also the material with which fractionator and various working parts should be made is also taken into consideration to resist corrosive materials. So prerequisites for high pore and high metal and high nitrogen crude. So high pore crude tank should be heated. So if we do all the processes at high temperature, so 4 point should not be a problem. High metal, so demetallization can be done using various catalysts and crude blending can be done. And if nitrogen content is there, so demetallization, basically denitrogenation using various catalysts as we have discussed in the previous parts also how nitrogen can be removed, sulfur can be removed, so all that can be done. So conventional flow sheet is we take the heavy crude into the distillation unit or sometimes the distillation unit is directly treated if there is if the viscosity is very high, large amount of impurities is there. So we sometimes skip this distillation unit and directly take this for the treatment. So in the distillation, we get if there are some lighter products, we get it in, as commercial as gas. And in the primary steps, what treatment is done? Hydro treating can be done, hydro cracking can be done, fluid cracking can be done, coking, and So in hydrotreating, these methods can be used. Hydrocracking can be done. Fluidized cracking can be done for coking, fluid coking, delayed coking can be done, and hydrovis breaking can be done. And also, uh, solvent deasphalting can be done to remove asphaltene. And further, the products from these primary steps can are sent to the secondary step, that is hydroprocessing is done, that is addition of hydrogen can be done to add the value to the product. And these, after the secondary step, the products given out are taken as commercial fuels. So difficulties in conventional refining is diluent is needed, that is expensive, means a large amount of solvent or diluent is needed. Higher pumping cost is required, expensive generation and recycle, supply concerns because due to high viscosity, heated pipeline because viscosity is very high, pour point is a problem. So pipelines, the temperature is required, high capital and operating cost, low reliability, and very high viscosity, so shipping problem is there, high metal, so refining problem is there, high Conradson carbon ratio, so that is also a problem, high carbon ratio, so need expensive hydrogen. So oil, so there is this solution that is uh, that was taken out, that is oil head processing of heavy crude oil can reduce the transportation and refining cost. So, what is oil head processing? It is basically the processing, some amount of refining or some amount of purification or processing is done before transporting this heavy crude oil to the refinery. So, some techniques are these are some of the techniques, that is heavy oil upgrading technology. So, what happens is this is the main reactor. So, the feed is taken here, and by contact, this is a here sand packing is there. It is a packed bed consisting of heated sand. So when we introduce a heavy crude oil in this, treatment is done and the lighter fraction is given out from here, and this sand is taken here for regeneration, and and here cyclone separator is there. So after the treatment of this hot sand with the crude oil, it is taken here where separation of this lighter fraction is done from here, and the sand is sent back. Sand is just a second. Sand is regeneration of the sand takes place and it is sent back to the reactor, and the lighter fraction it goes to the distillation column and gives out various cuts, various light cuts, and the heavier fractions. And after the treatment in this reactor, these fractions are taken to the RTP product, and this product is taken further to the refinery for rapid thermal processing. After rapid thermal processing, this product is sent to the refinery for further treatment. So with this procedure, some amount of problems are reduced, such as some viscosity may be reduced, or viscosity may be reduced, and some impurities are also are also removed in this case. The process is based on circulating transport bed of hot sand to heat the heavy feedstock and convert them to lighter products. So basically, what I told, the heat sand bed is interacted with the heavy crude oil, and further with the this heat treatment, it is converted to lighter products. So is a unique thermal cracking technology, and as the only heavier molecules in the residue are thermally cracked in this a selective thermal cracking procedure. Upgraded product does not require diluent. So the product from here, which the product which we get, it does not require diluent or blending agents to move it through the pipeline. So basically, we can say that the viscosity is decreased. Byproduct energy is used. So if some amount of energy is released, which can be used to generate steam or power. Small scale is appropriate to grow field sited upgrading capacity along with resource development. Minimum scale of 10,000 to 15,000 barrel per day. So another technique is improved delayed soaking unit. IDCU has revolved. can upgrade low API crude at the wellhead, tar sands, and bitumen, heavy oil, and other. It can these are the basically feedstocks: wellhead, tar sands, bitumens, heavy oil, and other heavy feeds. Improves coker efficiency, profitability, reliability, and safety. Handles virtually any pumpable hydrocarbon feed. So the difference with this, why it is improved delay cooking, because greatly reduces the cooking cycle. So the in delayed cooking cycle, the residence time was 18 hours, but here it is 16 hours. Therefore, it is called improved delayed cooking. Reduces coke yield. Here, coke yield is also reduced and significant heat recovery force. And the heat, which is byproduct heat, can be used for steam production. So this is the flow sheet for improved delayed cooking. Here we can take the heavy crude along with the steam, and it is heated here. Further, it is sent to the flash drum where the lighter gas off gases are given out from here, and the coke feed is taken to another heater where it is sent to the coke drums. It stays here yielding the for some time, giving the off gases which are sent to the fractionator. And on fractionation, the lighter crude oils are given from here. Off gases are given from here, and some lighter products are given from here. And in the coke drum, which releases, and the products pipe and the heavier products from coke drums are taken from here, where heat recovery takes place, and the heavier products are given out as pitch. Another kind is genoil hydro GHU upgrading process, which is genoil hydroconversion upgrader, is a hydroconversion process, conversion and hydrogenation in one step. It is applicable for pure acidic heavy crude and heavy refinery feedstocks. Proprietary devices are required to mix the hydrogen and the hydrocarbon stream. So this heavy crude is mixed with the hydrogen. Upper saturation of hydrocarbon is done with the hydrogen. High conversion of feed under moderate. It is done at moderate operating conditions. Stable product at higher conversion level. Premium sweet synthetic crude product removes. It also removes the need of expensive diluent blending. If so, basically it reduces the viscosity. Therefore, the need for diluent is eliminated. Flexibility of operation is there. An upgrader is economical at 10,000 barrel per day capacity. Operating cost is lower than the existing cost. So basically, this is as I showed here. This is a conventional flow sheet, but after introducing the uh, just a second, oil head processing, this is the improved flow sheet. So what we do is the heavy oil is firstly sent to the oil head processing. Here processing is done, and then this is sent to the pipeline. Sometimes diluent is required, may or may not. Mostly it is not required, as we saw in most of the procedures. It is not required, but sometimes it is required. This product is mixed with the diluent, and from the pipeline it is sent to the refinery. And in the refinery, various procedures are done, such as with breaking, proofing, thermal cracking, hydrocracking, etc. is done to produce various high value and low value products, and also asphaltenes are removed. So that's it for today, the theory part. So let us move on to the assignment questions. Some of the assignment questions that I've prepared for you guys. Am I audible to you guys?
Yes, ma'am.
Okay. So let me start with the assignment questions, and it will be really good if you guys answer some of the questions. Okay. The first one is, which of the following is not a type of sweetening process? Anyone? Anyone? Okay, then let me answer. As we studied, sweetening procedure is basically sulfur removal procedure. So as we studied, basically caustic wash procedure is also there, doctor treatment is also there, Merox is also there, but the fourth one was copper treatment. So here we can clearly see that this is the correct answer. There is no such procedure like iron treatment. So now the second question is match the sweetening process with their reagents. As I told you, caustic wash procedure consists of sodium hydroxide, doctor treatment, sodium plumbide solution, and copper sweetening is cupric chloride. So the answer is P is 2, doctor treatment is that is Q is 1, and copper sweetening is cupric chloride. So basically P2, Q1, R3. And the third question, which of the following cake is used for the production of high-grade graphite electrode for application in electrical arc field? Anyone? Anyone knows the answer? So the answer here is, as I told, the sponge coke and the short coke, they are amorphous in nature and produced by the decomposition of heavier products such as asphaltenes. But this needle coke is produced by the polymerization of lighter products such as aromatics present on mild thermal cracking of the crude oil. So it has a structure, crystalline ordered structure, that is needle-like structure. So this has very good properties and used as electrode material. So the answer is needle coke. Coming on to the fourth question, which is this braking procedure is used to reduce the viscosity of the residual oil. The favorable condition for the soaker visc braking procedures are, as I told, for soaker visc braking, it is lower temperature for higher residence time. In this braking procedure, the feedstock is preheated to approximate temperature of dash by using visc braking tar. The answer to this is 335 degrees C. As I told that in the preheater, it is heated to 335 degrees C and the heat recovery is done using the visc braking tar, which is basically the byproduct. Not byproduct, we can say it is basically the heavier grade product, the residue left after the vacuum distillation. Vacuum distillation. In the visc braking procedure, sixth question, in the visc braking procedure, soaker unit is maintained at the temperature and pressure of. The answer is 440 to 460 degrees C and 5 to 15 bar pressure. Question number 7. Heavy oil upgrading technology HTLPM is based on, as we studied right now, it is circulating transport bed. Hot setback, hot sand bag is used here. Identify A and B in the following improved delay cooking unit. So after heating, it is sent here, which is the flash drum. As we can see, off gas is coming out here, and this is the fractionator. We studied right now, just now I showed you. So this is the delayed cooking unit. So this is the fractionator, and this is the uh, flash drum. So in the question, it is A and it is B. So the answer is A is flash drum and B is fractionator. Now let us come to some of the numerical questions. I would like to, I would, just a second. Just give me. Okay, then let's come on to the ninth question, which is a vacuum residue has the following properties. Condensation carbon ratio CCR is given 28%, API gravity is 8.5 degree API, and sulfur content is 2 weight percent. It is fed into a delayed cooker at a rate of 2 lakh pound per hour. Determine the production rate of gas, naphtha, VGO, and coke on the basis of empirical formula. If the sulfur is distributed in the gas, naphtha, VGO, and co-products as 25%, 10%, 45%, and 20% respectively, find out the concentration of sulfur in these products. So what? So all this is given a vacuum residue. A vacuum residue is given in which CCR, that is condensation carbon ratio, is given. API gravity is also given to us, and the sulfur content into the product is also given. And feed rate is also given to us, and the sulfur content in various products is also, and sulfur content is also given to us in various products such as gas, naphtha, VGO, and coke products. So these are the empirical relations which we will be using to, which are also given to us to solve this question. So what we have to find, we have to find out the concentration of sulfur in these products. The exact concentration we need to find out. Okay. So let us start. Let's make a table. Product yield, then weight percent, and this is the feed rate. So for gas, the formula is 7.8 plus 0.144, and combustion carbon ratio is 20. It is given in PCR percent, so we will be directly putting 20. Yes, okay, let me try this. Okay. Then for naphtha, it is 11.29 plus 0.34 into 20, and then coke it is 1.6 into 20. So here we will be getting 10.68. It is 18.15. It is 32. And for gas, it will be 100 minus these three. So it will be 10.68 minus 18.15 minus 32. So we will be getting 39.17. Total sulfur, let us calculate in feed. It is given 2%. So basically 0.02 of feed, which is given 2 lakh pound per hour, which will be giving us 4,000 pounds per. This will be calculated by doing 0.10, the amount of gas in feed. It will be this. So it will be giving us 21360 pound per hour. Similarly, 0.1815, $54,000. So these are the amount of gas, naphtha, coke, and gas oil in our feed. Moving forward, in the question as it is given sulfur distribution in gas, naphtha, vacuum gas oil, and coke, it is given. So we will be calculating the total amount of sulfur in gas. It will be, as amount of sulfur is 4,000, so it will be 4,000 into 0.25. It is 25% is given in the question. Naphtha is given 10%. Sulfur in VGO is given 45%, and sulfur in coke is given 20%. So what we have to calculate? We have to calculate the concentration of sulfur in these products. So let us come to it. Concentration of sulfur in gas. So the amount of sulfur in gas is 1,000 upon total gas is 21360 into 100. It will be given giving us 4.68%. In naphtha, so the amount of sulfur in naphtha is 400 and the amount of naphtha in the feed is 36300 into 100, which will be giving us 1.10%. So the concentration of sulfur in vacuum gas oil, so amount of sulfur in vacuum gas oil is 1800 and the total amount of vacuum gas oil is 78340 as we have calculated here. This is the vacuum gas oil into 100. It will be giving us 2.29%. The concentration of sulfur in coke. The sulfur in coke is 800 upon total coke is 54,000 into 100, which will be giving us 1.25% sulfur in coke. So the answer is in gas it is 4.68%, in naphtha it is 1.10%, in gas oil it is 2.29%, and in coke it is 1.25%. Is it clear? Am I audible? Hello? Is the
Yes,
question
ma'am.
clear to you all? Okay, then let me move to the next question. The next question says, gas oil with API gravity of 35, which is one barrel contains 306 pounds, and a sulfur content of 2 weight% is fed into a hydrotreater. So the API gravity is given 35. One barrel is 306 pounds is also given, and the sulfur content is 2 weight% in a gas oil. So it is required to carry out HDS, that is hydrodesulfurization, at a severity of 92%. Calculate the hydrogen required and the API gravity of the product. The amount of hydrogen required can be calculated using this correlation. So which is STF hydrogen per barrel is 110.8 into SF, which is the weight of sulfur in the feed, which is 2%, and 10 for plus 10.2 into HDS, which is degree of severity, minus 659. The increase in the product API is calculated by this correlation given here, and the equation is used for feed sulfur content between 0.5 to 6 weight%. So we have 2% which comes in between them. So these two correlations can be clearly used. So let us assume one barrel of gas oil, API gravity is 35, which is one barrel is equal to 306 pounds. So amount of sulfur in feed can be given by this, which is 306 2.02 6.12 pounds per barrel feed. So let us come to the amount of hydrogen produced, which is given by the empirical formula in the question. So let us put the values. 110.8 into 2. SF is the sulfur content. plus 10.2 into degree of severity is 92 minus 659. After calculating this, is 501 SCF per barrel. The next part is the API gravity of products. So delta API is given by the relation 100,297 into SCF H2 per barrel minus 0.11205 into API of feed plus 5.5419. So let us put the values. If I is given in the question, API gravity, it gives us 3.1081. So this is the delta API. So API of product minus API of feed, 3.10812 on API of product minus 35. So API of product will be 35 plus 3.10812, which will be giving us 38.1081. So the answer is 501 SCF per barrel and 38.10 API. Is it clear? Let us move to the next question. Crude oil distillate impurities may be removed by chemical reagents. And so impurities can be removed by catalyst also, by absorption of clay also, and by caustic sweetening also. We know all these things. So answer is all of these. So by catalyst we can reduce metals, or we can remove metals by absorption of clay, as it is done of HT. What is the HTL process is done by absorption of clay. Sulfur removal is done by caustic sweetening. So we can say all these procedures can be used for the removal of impurities. Coming on the 12th question, C2H5 dot plus C6H14 gives A and B. So what is A? So this is basically a this breaking reaction. So what is done? This will be becoming a stable product, that is C2H6, and it will be giving C6H15 dot. Sorry, C6H30. One hydrogen will be going from here to here. The answer is first one. The next question, what is the name of ABC? So these are different types of coke. This one is the sponge coke. This is the short coke, and this is needle coke. Gasoline can be calculated using the empirical relation. We have seen in the equation. So this is the equation, which is the third one, 11.29 plus 0.343 into weight percent of Conradson carbon ratio. Now let us come to another question. 15th question, which is vacuum residue has Conradson carbon ratio CCR, that is 28%, API gravity of 8.5 degree API, and sulfur content of 3%. It is fed into delayed cooker at a rate of 4 lakh pound per hour. Determine the production of naphtha in percentage. So naphtha basically it is gasoline. So it can be calculated by the similar correlation. Naphtha percent is given by 11.29 plus 0.343 into weight percent of Conradson carbon ratio. Conradson carbon ratio is given as 20. So after calculation, we get it as 18.5. Production rate is 18.15. Coming on to the next question, vacuum residue has Conradson carbon ratio of 28% and API gravity as 8.5 degree and sulfur content as 3.08%, which is a similar question. But here, just a second, I guess I've done something wrong in this question. Something is missing. Just a second. Let me do it. Production of coke, basically, it will be. Sorry for this inconvenience. So the question here is this change. It is the production of coke in percentage. So the correlation for coke yield, it was given here. Let me come to it. The correlation here it is 1.6 into weight percent of CCR. So coke yield basically it is 1.6 into weight percent of CCR. So it is 1.6 into 20, it will be giving 32. So answer is 32. The production of coke is 32%. Coming on to the next question, which is gas oil with API gravity of 40. One barrel contains 306 pounds and a sulfur content of 1.58% is fed into a hydrotreater. It is required to carry out hydrodesulfurization at a severity of 80%. Calculate the hydrogen required. Similar question we have done in this question. It was similar, but one more thing was asked: API gravity of the product. So in this, we have to only calculate the hydrogen produced. Yeah. I forgot to write the correlation, so I will be writing here in myself, and further I will add it in the slides for your convenience. So sorry for this inconvenience. So the correlation basically it is given as HCl per barrel, HCF H2 per barrel. It is given as 110.8 into SF plus 10.2 into HDS percentage minus 659. So this is the correlation which is given. It is given in the question. This is the percentage of sulfur content and this is the degree of severity. So after putting the values from the question, it will be 1.5 into 10.2 into 80 minus 659. So after solving, we will get 323.2 SCF per barrel. So answer is 323.3 SCF per barrel. Is it clear?
Yes, ma'am.
Okay. I will add these correlations while uploading these slides, so don't worry about it. So let us come to the next question, which is also the last question for the day. So it is given it is required to decoke a breaker foam with an inside diameter as 7 centimeter and 900 millimeter long coil. So the distance and the diameter, sorry, length and the diameter of the coil is given with a coke layer of 0.38 centimeter thickness. This is done in two steps. The air is introduced to combust the coke layer, whose density is 100, 1138 kg per meter cube, and steam at 425 degrees C and flow rate of 5000 kg per gram. 3000. It is 3000. 3000 kg per hour is introduced to the coil to remove debris and cleaning up. The exit temperature is 800 degrees C. Coke contains 88 weight% carbon and 12 weight% sulfur. For how long should steam be switched on in hours? And some assumptions are given. Specific heat of steam is 2.42 kilojoule joule per kg degree C. And heat of carbon combustion is 31,780 kilojoule per kg. And heat of sulfur combustion is 8800 kilojoule per kg. So what is given here? It is a breaker coil basically. Basically, it is a coil, long coil, whose diameter is given to us. It is 7 centimeter. And moreover, all along there is a coke deposition which is done. And its thickness, deposition of coke thickness is 0.38 centimeter. And the length of the coil is 900 meter. Mean, however, it is 900 meter. So firstly, what we will do, we will calculate the volume of coke layer and then the mainly we need is the mass of coke layer. Considering it as a cylinder, volume of coke layer can be done by pi DLH, which is 3.14 into diameter is 0.07. We are taking it in meter. Length is 900 and height is 0.3. Sorry, in meters. Okay, in meters it is, so it will be into 10 to the power 9. So after calculation, we get it 0.751716 meter cube. So now the density of coke is also given, which is it is given here. So by using this density and volume is given, we can calculate the mass of coke layer. So what is done? Firstly, the air is introduced to combust the coke layer. So basically, this air, when it will combust the coke, some amount of heat will be generated, and this heat is further used for the generation of steam. So basically, here we have to do is the heat balance. So the heat released by air to combust the coke is taken by the is taken for the generation of steam. So basically, we will be doing is the heat balance. So we got the heat mass of coke layer. So heat of carbon combustion in coke. The amount of carbon in coke is given 88%. So it will be 0.88 into the mass of coke and the heat of combustion of carbon, which is given in the question, that is 31780. It will give us 23.92 into 10 to the power 6 kilojoule of energy. Kilojoule of heat is used in the combustion of carbon in coke. Likewise, heat of sulfur combustion in coke. Amount of sulfur in coke is 12%, so 0.12 into mass is 855.4528, and heat of sulfur combustion is given as 8800 kilojoule per kg. So it is taken as 8800, which will give us 0.903 into 10 to the power 6 kilojoule of heat. So total heat of combustion in coke is, by adding both, heat of carbon combustion, that is 23.92, plus 0.903 into 10 to the power 6, which will give us 24.823 into 10 to the power 6 kilojoule of total heat is produced. So rate of so this is the heat produced by air combustion of from air. So rate of heat gained by, so now this heat will be used for the production of steam. So rate of heat gained by steam will be mCp delta T, which is P out minus T in. P out minus P out and T in is given. So specific heat of steam is given as 2.42, and mass, that is flow rate of steam, is 3000 kg per hour. So MS is flow rate, which is 3000. Specific heat is 2.42. P out is 800 degrees C and T in is 425 degrees C. So after calculation, we get 2.7225 into 10 to the power 6 kilojoule per hour. So this is the heat gained by steam. This is the heat given by air for the combustion of. This is the heat given after the combustion by air of coke. So the time required for switching steam can be calculated by this divided by this. This is the total heat given, and this is produced in 1 hour. This amount of heat is gained by steam for 1 hour. So this total heat divided by heat used in 1 hour will give us the time for how long steam needs to be kept. So it is 9.117 hours. So answer is for 9.117 hours, 9.1 hours, steam needs to be switched on. Answer is 9.1. Is this clear to you?
Yes, ma'am.
So we are done for the day. These are all the questions for the fourth tutorial.
Ma'am, can you please show second and 10th question?
Just a second. 10th question. So this is the 10th question. This one only, na?
Yes, ma'am, and second also.
10th question, this is first part and this is second part of 10th question.
Oh, yes, ma'am.
Okay.
Yes, ma'am.
And which question? Second, right?
Yes, ma'am.
Okay, this is the second question. You can access these slides. I will be uploading
12th also, please.
I will be uploading the video recording also on YouTube. You can search it using my name. Just a second, question. And moreover, these slides will also be uploaded, so you can get these questions from there also. Any other question?
No, ma'am, thanks.
Okay. Then let me use that. So, is today's class clear to you all?
Yes, ma'am.
If you guys have no other questions, so we can end today's session. Should I leave the class? Should I end the class?
Okay, ma'am.
Okay. Okay. Thank you, everyone. Okay. Bye.